And we're back, and I wanted to go through a potential well problem. Uh, these are the things where you have diagrams of potential energy versus a function of position. It basically is talking about trying to measure energy between two particles that are different distances apart from each other, or possibly the forces between the particles at certain distances. And lots of information can be gathered from diagrams like this. And here's an example. This is the potential energy as a function of position. And the way we think of this physically is you have an atom fixed at the origin, and then you have a second one that you're able to move around at different distances from that one at the origin. Okay? And you're basically just determining how much energy is there. Is it attractive or repulsive? What's the strength of the forces, the magnitude of the energies, and so on. Now, some of the things you can gather from this are equilibrium positions. Okay, at certain distances, if you were to put the two particles that distance apart, there would be no force. They would just sit there. Okay, but those can be stable or unstable. We'll get to that in a minute. Then mathematically, there's this connection between the force and its associated potential energy. And it's related through this derivative. It's called a gradient. And basically it's a derivative with respect to position. Now forces that follow this relationship are what we call conservative forces. This is true for gravity, electrical forces, elastic forces like springs, rubber bands. It is not true for friction. Those are called non-conservative forces. Okay, and the minus sign in there it has to do more with direction than anything. Okay, but it's probably best just to hit the example. This is the infamous Nike problem. Where they give some weird function here that gives the Nike swoosh. And this is similar to actual potential wells that you have for particles and the interactions between the particles. So, yeah, if we have the equation, we could just go ahead, we can take a derivative. That's not such a big deal. We've got this minus sign out front. And so if we look at our energy equation, the first term will just be these constants. R to the first becomes R to the 0th, which is 1. And then we have this next term, R to the minus 1. The minus 1 comes out front. And we subtract 1 with R to the minus 2 power. And when we bring the minus sign inside, we have our force equation. Actually, the second term is going to be positive with AB over R squared. Okay, so we've got this force equation here, and we could just go ahead and graph it if we wanted to, or we could also take a look at the energy graph and consider the fact that what this gradient does, what it really is graphically, is the force is the negative slope of this energy graph. So for example, over in this region, to the left of this R0 value, you have a negative slope, and it's pretty steep. Well, the opposite of a negative slope is a positive number, so that the force actually starts big and positive, and it comes down, oops, if I can draw, comes down and it hits at this R0. Okay. Now this R0, if you think about this position, that's this minimum, that's the bowl of this graph. And at that location, your tangent line is flat, okay, no slope. If there's no slope, that means the force is 0. That's an equilibrium position. But now if we look at this, in this other region to the right of equilibrium, you have a positive slope. And it basically approaches a constant. So what that means is that the force goes negative. Okay, the opposite of a positive slope is a negative number. And it's going to approach some constant value. there's actually almost like an asymptote down here. And the force approaches that as you get far away. Does that relate to the force equation? Well, it does. When r is small, this second term, this positive term, is big and positive. Okay. At some point, you have zero force. Okay, so what's that look like? When force is zero, that means that a over b is equal to ab over r squared. Okay, the a's go away, and r squared is equal to b squared. So that would be our equilibrium position, wherever this b constant is. Okay, and then as r gets big, when these two particles get far apart, the second term basically drops out. It approaches zero, and you approach a negative constant. So that tells us what this asymptote is down here. Okay, it's a force that you approach far away. Okay, now, so here we have both the math, if we know the function, you can do it that way, or you can sketch the graph of the force if you just know what the energy looks like. Now the other thing about these are these equilibrium positions, stable versus unstable. Now in this case, if you're to the left of equilibrium, so if your two particles are close together, you have a positive force, which means your particles are repelling. Okay, so the second particle is being pushed away from the origin. But then, to the right of equilibrium, you have a negative force, which is an attractive force. So out here, the particles are attracting so that second particle is being pulled towards the equilibrium position, or towards the origin. So either way the second particle goes, it's going to be pushed back to equilibrium. That's what we call stable equilibrium. Okay, this would be like a spring. Okay, if you displace a mass on a spring, stretch it or compress it, it's going to bounce back to equilibrium. That's where it wants to go, and it oscillates. So this is basically showing an oscillation. The equilibrium distance in a chemistry class, you might call that the bond length. Okay, so atoms that form molecules, they're stable equilibrium positions, and atoms are vibrating. They're oscillating back and forth. They're in the bottom of this potential well. Okay, it's like a bowl, and you're going to rock back and forth if you put a marble in a bowl. So there's a few different ways we can kind of picture these things. This gives us the gist of what potential wells are like and what you can do with them. And so, again, I hope this helps, and until next time, we'll see you later.